Okay, kids, we're back. I hope you had some time to review the grade 11 material that I put up and maybe look at some of those videos to get your mind back up to speed about all things electric. All right. So today we want to focus in on Chapter 7, Section 2, which is about electric force. So we're mostly focusing in on electric force. We'll eventually get to electric field, but electric force. Now, we've spent a good portion of this course in kinematics, dynamics, circular motion, momentum, a variety of different topics. And these topics have always sort of revolved around gravity. So we're going to actually use gravity as a springboard, a launching point to help us understand electric force. So we're going to use a force that we're very familiar with now because we've done a lot of work with it to help us understand this new one. So let's go through this. So we know that gravity is caused by a property of matter called mass, and it's measured in kilograms. Because matter has mass, we have gravity. And one of the interesting things that we have seen is that mass has attraction for other mass. And the more mass there is, the more attraction there is. Remember the equation, uh, F big G is equal to big G M1 times M2. If M1 and M2, one or both of them are bigger, larger mass, larger force of gravity. That same equation, that same equation tells us that the greater the distance between the masses, the less the attraction. And that all comes from this equation right here. F big G, well, at least the magnitude of it, is equal to the gravitational universal gravitational constant, however you want to say it, the mass of one object times the mass of the other object, all divided by how far they are apart from each other, center to center squared. And associated with this, we have a gravitational field. So this gravitational field is different than gravitational force, right? Different equation, different concept. And it says that around any object, because that object has mass, let's say its mass is big M, all right? Around it, beyond its physical limits, out here, there is a field, which we call gravitational field. And here's the equation for it. And the gravitational field is showing us a direction because it's a vector field. What does that mean? Well, it means that if you were to put a tiny bit of mass here, and we'll call it a small test mass right here, that test mass would feel an attraction towards the mass which is creating the gravitational field. That's why the gravitational field has this direction. And I want to remind you, this is very important, that the unit for the gravitational field is newtons per kilogram. So it's basically telling you, hey, this gravitational field applies a certain number of newtons worth of force for every kilogram that is present in the small test mass. Right? That's what it's telling you how strong this gravitational field is. Think about it near the surface of the Earth. The magnitude is 9.8 newtons per kilogram. Think about what that's saying. 9.8 newtons worth of force is going to be present for every 1 kilogram of mass. Well, what we're going to do now is go through a very similar discussion that we did for gravitational force, but now for electric force. So what's electric force caused by? It's not going to be caused by a mass. No, it's caused by a property of matter called electric charge. And electric charge is measured in coulombs. C. Probably remember that from grade 11. The difference here with electric force is you can have attraction like you do for gravitational forces, but now you can also have repulsion. And that's because electric forces, which are caused by electric charges, right? Electric charges come in two kinds. So because they come in two kinds, you can have attraction or repulsion. If it's positive charge and another positively charged object, repulsion. Negatively charged object and another negatively charged object, repulsion. Positively charged object, negatively charged object, attraction. Different. Different than gravity. What is the same, though, is, and it would make sense, I think, common sense, sort of a gut feeling, just like if you have more mass involved with gravitational force, if you have more charge, and remember, charge is measured in, let me write that down right here, the Coulomb. All right, so it's not measured in kilograms, measured in coulombs. If you have more charge, more coulombs of charge, well, you're going to have more attraction or repulsion depending on the case here. That kind of makes sense, I think. We can buy that. Next, the greater the distance between charges, the less the attraction or repulsion. Okay, yeah, if they get farther apart, the interaction won't be as strong. I can see that. I can see that. All right, so that's similar to gravity. So we have some similarities, we have some differences. So we're ready now to establish not F big G, but F big E, not gravitational force, but electric force, at least the magnitude of it. And it has not big G, but K, not a universal gravitational constant, but an electrostatic constant. Look, 9.0 times 10 to the 9 newtons meters squared over coulomb squared. So it's not G anymore. But look at the similarity in the units. You see, G has this unit right here, and it's basically telling you the force that is going to be produced depends on how far apart the objects are squared and multiplying two masses squared, kilograms times kilogram. Look, the electric force that's available depends on how far apart the charges are squared divided by multiplying, look here, don't multiply two masses together, multiply two charges. How much charge does object 1 have? Q1. How many coulombs are in object 2? Q2. So instead of multiplying two masses, we multiply two charges. Coulomb times coulomb. Look down here. Coulomb squared. And look at the shape of this formula. It's very similar to gravity. But it recognizes that it's not gravity, so we don't have a gravitational constant, we have an electrostatic constant. This force, electric, is not being caused by mass, it's being caused by charge, so coulombs times coulombs, and it also depends on how far apart these objects are, and that distance is r, and once again, r is still center to center. That has not changed. So there's even a similarity in the look, the feel of the equation. Very interesting. All right, so in a way very similar to gravity, we can say that if you have a particle, an object, and there's a charge on it, just like we can say, hey, there's an object and it has a mass, m, but now we're going to say here's a particle or an object and it has a charge q, but now we have to make a decision. Is it a positive charge or a negative charge? Well, let's say it's a positive charge. Then we understand that just like outside an object with mass, there is a gravitational field. Outside of an object with a charge, in this case a positive charge, there is a gravitational field. And to find out the strength and the direction of that gravitational field, we would put a test charge here, just like you would put a test mass around a massive object to see if there was a gravitational field. The only problem here is when you're putting a test charge there, you have to decide, am I going to put a small positive test charge there, or am I going to put a small negative test charge there? Either will work, but if we're going to establish coherent theory and equations and mathematics to electrostatics, we have to pick one of them. And a long time ago, this was done. So all electric fields can be tested by using a small positive test charge. That's the way it was established. So if you want to investigate the electric field around a positively charged object, you would put a small positive test charge there. Positive and positive repel, so this small positive test charge would feel an electric force away. There would be a repulsion there. The arrow was pointing out. And I could maneuver this small positive test charge anywhere around the charged particle I'm investigating, trying to figure out its electric field, and I would always have repulsion. So therefore, by definition, the electric field outside a positively charged object always points away. Look at these blue arrows. They're always pointing away. And that direction is established by definition of using a small positive test charge to analyze an electric field. Similarly, if we wanted to investigate the electric field around some object, and let's say that object has a certain amount of charge, Q, so many coulombs, all right? But now we know that it has a negative charge, all right? It has a negative charge. We would want to investigate the electric field around it by employing a small positive test charge. So here it is, a small positive test charge right there. And I could find out what electric force would this small positive test charge experience. Well, it would experience a force of attraction towards the negatively charged particle. So upon investigating the electric field around this negatively charged particle, the electric field would always cause attraction for this positively charged particle, so I could go about and map the electric field around this negatively charged particle. All right, I could map it out, and I would always see there's attraction. So the arrows of the electric field would always point towards the negatively charged particle. Therefore, by definition, the electric field around a negatively charged particle is always pointing towards the definition, towards the negatively charged particle by definition. So what am I saying here? I'm saying these directions here, positively charged particle, the electric field points away. Negatively charged particle, the electric field points towards. This has all been established because when scientists decided how are we going to test the presence of electric fields, we're going to use a small positive, positive, positive test charge. And once that decision was made, everything else fell into place. These directions for electric fields were established, and that's the way it is. Now you can say, oh, I wanted them to use a negative test charge. Well, good luck to you. No one else does that. That's simply the way it works. Next, let's take a step back to something we're familiar with, the gravitational field around an object. G, arrow, we're finding the magnitude here, is equal to big G times the mass of the object all over r squared, and the unit is newtons per kilogram. Well, similarly, just make the transfer. Instead of a gravitational field, we're finding out about an electric field. Instead of the universal gravitational constant, we're going to use the electrostatic constant. Gravity is caused by mass. Electric fields are caused by charge. So instead of a mass m, we've got a charge q and so many coulombs. Divided by r squared, r squared. All right, so if you want to find out, for example, if you want to find out the electric field right here, you would need to employ the electrostatic constant. You would need to know how many coulombs of charge are in the particle that we're testing the electric field are of, and what is the center to center distance between them, and you could find the electric field right at that point. And since it's a positively charged particle that we're testing here, we would know that the direction of the electric field would be away from it by definition. Okay, well, let's try an example. Let's see what we got here. This is our first example. And let's say that right here, we've got a charge, and we're going to call it Q1. And let's say the charge on Q1 is a negative charge, negative 8.6 times 10 to the negative 5 coulombs. And let's say that right here, we've got a charge Q2, and the charge on Q2 is positive charge, 5.0 times 10 to the negative 5 coulombs. And let's say that right here, we've got a charge Q3, and it's a positive charge, positive 6.5 times 10 to the negative 5 coulombs, right there. Now, let's talk about some distances that we have here. Let's say that the distance between charge 2 and charge 1, which we're going to call R21 or R12. Let's be consistent here. Let's call it charge 1, 2. Let's fix that right now so we're consistent. Charge 1, 2. The distance between those right there is 0.52 meters. Okay, that's the distance right there between those two charges. And the distance between charge 2 and 3 right here is 0.3 meters. Now what do we want to find? We would like to find the electric force on charge Q3 that is being caused by the presence of charge Q2 and charge Q1. So that's kind of important to realize now that an electric charge on an object can be caused not just by the presence of another electrically charged particle or object, but by more than one. That at this spot right here where Q3 is, it's going to feel a force of attraction towards Q1. So that's what I've drawn here in green. Force electric, right, of charge Q1 on charge Q3, and it's an attractive force. That's why I've drawn the arrow from Q3 to Q1. But at the same time, charge Q3 is going to feel an electric force because of the presence of charge Q2. All right? Now, these are both positively charged objects. So the electric force of charge Q2 on charge Q3 will be repulsion. That's why I've drawn this yellow arrow away. You see that? So I haven't done any calculating yet, none at all. I'm just trying to get the lay of the land here. Hey, there's going to be attraction here from charge Q1. Hey, there's going to be repulsion here from charge Q2. That's all I've done. No calculating yet. So now what we're going to do is we're going to find the magnitudes of the charges we just talked about. And we're going to employ the equation we just learned. K, charge on one object, charge on the other object, divided by how far apart they are squared. How far apart they are squared. So how are we going to do that? Well, the first thing we want to do is find the magnitude of the electric force between charge Q2 and charge Q3. So we would put in K, Q2, Q3 divided by how far apart they are. So that's R23 squared. So you put those values in there, Q2, Q3 divided by R23 squared with the electrostatic constant. You put that in there and you would get this value right here. Now I want you to pause the video and actually try to do this. It's good practice for you, and see if you get that value right there. So pause the video, use this equation that we just learned, and use it to establish the force between Q2 and Q3, knowing the charge on Q2 and Q3 and how far apart they are. So that's what we want you to do. Next, we want to find the electric force between Q1 and Q3. So we're going to use this equation again, K, electrostatic constant, but now we're going to put Q1 and Q2 in here, but now we've got to put the distance between Q1 and Q3. What's that distance? Well, kids, you all know Pythagoras, right? You can figure that out. It's a right angle triangle. You can figure out what this hypotenuse is, put it in there, square it. So actually do this. It's good practice for you. And see if you get the magnitude to be what I have right there. So pause it, try it, and see what value you get, okay? All right, so I hope you did that. I hope you got those values, and we're back. So let's reestablish what we're talking about. We want to find the total electric force, I beg your pardon, on charge Q3. So the total electric force on the charge Q3, and that is going to equal the electric force from charge Q3 on charge Q3, so that'll be part of our calculation, plus the electric force, that's an ugly looking E, let me fix that, goodness gracious, there, that's better. The electric force from charge Q1 onto charge Q3, so it's a sum of these. But we just can't add 325 and 140 and just, oh, that's the answer, I'm good. 465er. Nope, we can't. We're adding vectors. Look at that. We're adding vectors. I know when I add vectors, I like to use components. So what we have to do is break down each of these vectors, which are electric force vectors, into their components. So let's do the first one. Electric force on electric force from charge Q3 onto charge from charge Q2 onto charge Q3. I better get that straight. And I've drawn it for you right there in red. We know it's a repulsion that is straight up along the y-axis. So we know that there's no x component to this. It's all y component in the positive y direction. So I can put that in right there. It's all y. And if you want to go back and look at the diagram we originally had for this, you would see it's all in the y direction. So that first one is easy. Next, the electric force from charge Q1 onto charge Q3 is along that hypotenuse I asked you to calculate. Right there. Right there. And if you go back and look at what we had before, I showed you a calculation that showed that this was 60 degrees in here. That was 60 degrees. Why don't we just take a quick look back up here. See what I did here? Theta right in here is tan inverse of uh, the opposite 0.52 right here over the adjacent 0.3 right there. So 0.52 over 0.3, we get 60 degrees in there. So I didn't mention it before, but it was there for you. So if I know that's 60 degrees in here, and I know the magnitude of this is 140, right? I know the magnitude. I know this is 140 newtons along the hypotenuse. I can use that 60 degrees to find the y component of this electric force and the x component of this electric force. And I know you all know how to do that. I take a look at the x component. Look, it's positive. So I put in the positive value there, right? And this side is opposite to the 60, so we'll be using sine here. And I get positive 121 newtons x hat. Here, I look at this force. This y component is towards negative y, so I put a negative sign in there. And it's adjacent to the 60, so I'll use cos here. I'll use the cos of 60 on the 140, and I'll get negative 70 newtons y hat. So now finally I can add this and know that the total electric charge, excuse me, the total electric force on charge Q3 is given right here. Positive 121 newtons X hat plus 255 newtons Y hat. Use components, very powerful. The other thing that we learned here is that the electric charge, the electric force on a charge, in this case charge Q3, is equal to the sum of these two other electric forces. The electric force from charge Q2 on Q3 and the electric force from charge Q1 onto Q3. So you have to add them to get the total electric force on charge Q3, and we added by using components. So listen, have a good one. Take care of yourself. I did call some of you. I was able to find some cell phone numbers, individual student cell phone numbers for some kids. So I didn't call all of you because I just couldn't get the cell numbers for all of you. And some of you I called and didn't answer because it comes up as unknown caller. But that was me just checking in on you kids, trying to see how you're doing, getting feedback from you and stuff like that. I've left you some homework to do on electric force. Remember, components are our friends. You guys take care. We'll see you soon. Bye bye.